Next, we need to talk about measures of spread. We just got done talking about measures of center, which again tell us a little bit about what's going on in the middle of a set or what's typical in a set. With measures of spread, they're pretty much exactly what they sound like. They tell us how spread out a data set is. We'll see what we mean by that right now. We'll start with range. Range is probably the simplest measure of spread. We're just going to define it and move on. Range is simply the maximum value in a data set minus the minimum value. Very simple. It's just the difference between the highest number in a set and the smallest number. So for instance, if we were looking at example 9, which we're going to get to in detail in a moment, but you can see the highest number is 86 and the lowest number is 74, and therefore we would have a range of 12. In class B, the range is a lot bigger, from 64 to 103. That would be 39, I believe. That's pretty much all you need to know for range. When it comes to variation and standard deviation, a lot of students freak out about standard deviation and variation on the SAT. They think there's a lot to know about variation and standard deviation for this test, and there's not. You don't need to know formulas for variation and standard deviation. We are in a moment going to talk about how we can use a fairly good calculator, a graphing calculator, calculator that can perform statistics calculations, how we can use those kinds of calculators to produce a standard deviation. But again, in most cases, you don't need to know exactly how to calculate a standard deviation. You just have to have a sense of what variation and standard deviation are. And again, because these are measures of spread, they do tell us how spread out a data set is. If you actually look at the words variation and deviation, the words themselves, the typical everyday definitions of those words, should give you some idea of what these words mean in statistics as well. They just tell us how much variation there is in the elements in a set, how much each of the individual elements deviate from those measures of center that we just talked about, namely the mean. So for instance, if we take a look at example 9, if you already understand variation and standard deviation, you can obviously do example 9 on your own, pause the video, and then come back and join us. You can use the calculator on example 9. We are not going to use a calculator. We're going to see that there's really just no need to use the calculator at all. So if we take a look at class A and class B, you notice that their measures of center are all exactly the same. Some people might look at mean, median, and mode, see that they're all equal, and think that these two sets are very similar to each other, and in terms of measures of center, they are. However, you can see that class A's scores, if you look at the mean here, 82, class A's scores are clustered more closely around that 82 than class B's scores are. So for instance, you've got the 83 in class A that's right by the 82. The 81 is right by the 82. This is one above, one below. The 80 is 2 below. The 84 is 2 above. So again, these numbers, these points earned in class A, they tend to stick pretty closely to the mean. They tend to be clustered pretty closely around the mean. However, in class B, if you look at those scores, there is a much wider spread. There is much more variation or much more deviation from that mean. That mean is 82. You've got the 83 being fairly close to the 82. This one's 4 and 4 above. This one's way above, over 20 above. This one is almost 20 below. So again, the class B scores are much more spread out. So when it comes to what example 9 is asking, so we've got obviously the table summarizing the results for two classes. We do have equivalent measures of central tendency. The question is just asking which class has the greater variation in the distribution of scores, and of course, it's class B. As we said, class B's scores are not clustered nearly as closely around the mean as class A's scores are. So that's what variation is. It just has to do with how closely the scores are clustered around, or how far the scores deviate from the mean of the set. Some students do wonder if range and variation are exactly the same. They think that if a set has a bigger range like class B does, then the set's going to have a bigger variation. They are very closely related. They are not, however, synonymous, so just be careful of automatically assuming that if a set has a bigger range, it also has a bigger variation. That will not always be true. In terms of standard deviation and variation, they are both very rare on the test. If you do see a measure of spread being tested, there's probably a slightly higher probability that you will see standard deviation rather than variation. Again, on this test, you will not need to calculate a standard deviation, but what you should know is that variation and standard deviation follow each other directly. In other words, the higher your variation, the higher your standard deviation, and the lower your variation, the lower your standard deviation. So they are directly correlated. If we look at class A and class B and write down their standard deviations, the standard deviation of class A is 3.9. For class B, it's 12.1. And again, remember we said class B had a much higher variation in the distribution of the scores than class A, and of course that is why the standard deviation of class B is higher than class A. Now you may be looking at these numbers saying, wait, where the heck did you get those numbers from? Well, we use the calculator to calculate those numbers, and as we mentioned previously, you will not need to calculate directly a standard deviation from a bunch of numbers in a data set. Most of the time, what you're going to need to do is compare the variations or standard deviations in multiple sets, like we're doing here, like we did in the previous example. At the top of the next page, we're going to start talking about representing data visually using dot plots or histograms or distribution curves. Again, these questions are not extremely common, although you probably once per test will see data represented visually. I would say histograms are probably College Board's favorite. Let's start with dot plots. Dot plots, they're fairly simple. We mentioned these in a previous video. All a dot plot is, it's a way of representing frequencies. So basically we have on the horizontal axis, we will have a bunch of data values, a bunch of possible values for whatever we're measuring in our data set. And then above each of those values, we will have a certain number of dots or no dots at all, indicating that, for instance, here there were no 70 gigabyte data stored on any of these phones. Let's take a look at number 25. We're going to work through this. If you feel comfortable with dot plots and measures of central tendency and measures of spread by this point, you can obviously do this question on your own. The 26 students in a computer science class conducted an experiment in which they reported the amount of data in gigabytes stored on their mobile phones. The dot plot above displays the results. Which statement is an accurate analysis of these data? So you can see in the answers we're comparing a couple of measures of central tendency, measures of center, mean, and median. Look, there's two ways to do this question. We can do this question purely computationally, in other words, purely mathematically, and then there's a shortcut that we could know that would help us get through a question like this much more quickly. I'll show you how to do this computationally, and then we'll talk about that shortcut. I am going to need my calculator for this. So here's what we're going to do. First, let's take care of the median. If you've watched the previous video, you will know that we have a couple of ways of finding where our median is going to lie. In this case, one of the things that I could do to find out where the middle element is, although in this case, remember, that's an even number of students, which means we're going to have two numbers, two gigabyte amounts in the middle, and then we're going to have to average those two to find the median. So one of the ways that I could do this is I could go end to end and start crossing off the extremes. So there's one there, one there, one there, one there, one there, one there. But you can see this is going to end up taking quite a bit of time to do when I have 26 data points. So unless your set is maybe 5 to 10 data points, I would not recommend doing the end-to-end cross-off method to home in on where the middle elements are. I would use the sort of tricks that we talked about in an earlier video. What I'm going to do is 26 divided by 2, that equals 13. So what this means is we add 1 to the 13 to get 14. We know that our median is going to be the average of the 13th and the 14th data point, the 13th and the 14th member of this set. So now I'm just going to start counting out these dots. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So the 13th and 14th, 13th, 14th, they're both going to be 50s, which means my median is going to be 50 as well. In other words, my average of these two, obviously I don't have to write this down, but I'm going to. 50 plus 50 divided by 2 is 100 divided by 2, which is 50. So I know that my median is 50. Now, in terms of finding the mean, there is an efficient way to calculate the mean here. So what I'm going to do is I'm going to take the 30. I'm going to add that to how many 40s? 1, 2, 3, 4, 5, 6, 7, 8 40s. 8 times 40. I'm going to add that to 9. I shouldn't have to count all these up. I can see that there's one more 50 than there are 40. So that's 9 times 50. There's going to be 160. There's going to be 180. There's going to be 4 90s. And there's going to be 200s. I'll just write 200 there. And now what I'm going to do is I'm going to go right into my calculator. I'm going to add all of those up. I'm going to get a sum, and then I'm going to divide by 26, which is the number of numbers that I'm adding. So 30 plus 8 times 40 plus 9 times 50. Obviously, that's not a times. Obviously, you want to be very careful about these calculations. Make sure you're not skipping anything or repeating anything or putting in pluses where there's supposed to be times or vice versa. So 9 times 50 plus the 60 plus the 80 plus the 4 times 90. And then we are adding in that 200 at the end. And we get 1500. Again, we need to now divide that sum by the number of numbers that we added together to get that sum. So I'm just going to go ahead and divide by 26 and hit enter. So there's my mean. It's approximately, let's just round up to 58. So now that we have those numbers, we're done. We can see that the mean, so this is the mean right here, is 58. And so whatever answer says the median is less than the mean or the mean is greater than the median is going to be right. And right there we've got mean, which again we said was 58, median, which we said was 50. 58 is greater than 50, so our answer has got to be A. That's how you would do this computationally. And again, if you're acting very quickly and thinking very quickly and punching numbers in your calculator very quickly, this shouldn't take too long. I would say you could get this done in a matter of a minute to a minute and a half. In terms of how to do this a little bit more efficiently by knowing about the general shape of this dot plot would be to look at this as if it were almost like a distribution curve. Like we have something that looks like this, or you could even, I'm going to do this in a different color. You can even do this almost as if it were a long right tail. This really would be, we're going to talk about this in a moment, this really would probably be called a bimodal distribution rather than a right skewed distribution. But either way you look at it, what you end up seeing is that you've got a lot of dots clustered over here, but then you have these, I guess what you would call almost outliers. You've got these very high numbers. There's nothing in the middle, but there's these very high numbers. So what's going to happen is that your median is going to be somewhere over here. And again, you can sort of see that visually, but you could also probably just determine that the way that we did here. So you know your median's probably going to be in one of these stacks. But these elements over here, these numbers over here, are going to pull your average, pull your mean central tendency up, right? If I have, a bunch of 2s and 3s, let's do 2, 2, 2, 3, 3, 3, 3 in a set, the average is going to be somewhere in the middle of those. But if I start adding in maybe a 10 and a 15 to that set, well, then my average is going to be pulled up, right? My median will still be somewhere here in the middle. It'll still be like a 3, but my mean is going to be pulled a lot higher. So in the case of a distribution that looks like this, or even that looks, that's not right, or even that looks like this, again, your median is going to be somewhere here or somewhere here, but your mean is going to be pulled up by all of these elements here, or by the fact that you've got a lot of higher valued elements to the right of this hump. So if you are familiar with the way that distributions look, you probably could answer this question a little bit more quickly. I will say that I sometimes just like to do the computation just so that I'm not making any assumptions that are unfounded. In terms of histograms, histograms are extremely similar to dot plots. In fact, I call them here the bar graph equivalent of a dot plot. That's basically what they are. The benefit of a histogram is that we can get a lot more frequency onto our plot or onto our figure. With dots, you're not going to sit there wanting to write 100 dots above an axis, but with a histogram, you can change. So the y-axis, this is the frequency axis, and the x-axis is still the data points or data value axis. So what we have here is we have what we just did in the dot plot. We have this written on the histogram here. So we have 130 gigabyte data value. We have 840. We have 950. We have 160, 180. We've got 490s, and we've got 200s. By the way, it is occasionally a good idea to write the frequency values right above the bars, especially when you get to the bars over there on the right. Sometimes your eyeballs can play tricks on you getting back over there to the vertical frequency axis. So again, all we're doing here is we're representing on this histogram the data that we had on the dot plot above. And as I said, the benefit of the histogram is you can make some really, really big numbers on your vertical axis. I mean, this could have been 1,000, 2,000, 3,000, all the way up to 10,000. That's the benefit of a histogram over a dot plot. Probably would not be a good idea to draw 10,000 dots. You'd be there for a while. At the top of the next page, we got to talk about box and whisker plots. Again, these questions have popped up every now and then, and students do sometimes freak out when they see them. But these questions are very, very simple if you actually know what's going on in a box and whisker plot. Sometimes these are just called a box plot rather than box and whisker. So let's just go over the key points, key areas on a box and whisker plot. So what you're going to have down here is you're going to have your values. So I don't know, if this were a scale of let's say 5, maybe you'd have 5, 10, 15, 20, blah 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 blah. So you'll have your values down there, and then the box and whisker plot will have some little vertical segments and some horizontal boxes that will correspond to either a range of values or to a particular value. So for instance, I'm just going to start with probably the most important one here. Let's talk about this little vertical segment C. That is the median. That is the median of the set. So 25, 30, 35, 40, 45, 50. So in the example I'm giving here, our median would be 50 because that little vertical segment at point C corresponds to a data value of 50. That is the median of the set. The little segment that is in the middle of or within the box. So this is the box here. The middle segment, or as I said, the segment that is inside that box, that is your median. That is always your median. Now, in terms of the next easiest things here, these might be even easier than the median. A and B. A is the minimum value, and B is the maximum value. So in this case, we'd have 5 and some number over here, I don't know, 80, 85, something like that. Not going to calculate it because it doesn't really matter. The minimum and maximum value are at A and B. And obviously to find the range, we can use those two little vertical segments at A and B. The minimum and maximum, we just do max minus min, we get our range. In terms of D and E, let's talk about those next. D is we're going to call this the median of the lower half of the elements in the set, the data points in the set. The median of the lower half, and then E is the median of the upper half of the elements. So here, you know what? I'm going to give a quick example. So let's do 2, 3, 4, 5. Let's just make this simple. 7, 8. How many is that? That's 7 elements. So there's our median. That value, if we were doing a box and whisker plot, that 5 would lie at C. The median of the 3 elements, so this would be C. The median of the lower half of the set, the 3 elements to the left of the 5, would be the 3, so that would lie at point D. Obviously, that 2 would be point A because that's the minimum. The median of the 3 elements in the upper half of the set, the 3 elements that are greater than the main median, the actual median would be 6, 7, 8. So the median of those would be E, and then of course 8 would be the B. And this would be a perfectly symmetrical box and whisker plot just because everything is perfectly spread out here. We've got just, what do you call these? Consecutive integers here. So we would have a box and whisker plot that looks very, like I said, very symmetrical, something like that. In terms of F is known as the interquartile I don't believe you're going to see this term on the test, but just in case, this is called the interquartile range. Now, what does that word mean, quartile? Well, if you notice that box and whisker plot sort of splits your elements into 4 quarters, right? You've got the first quarter here, you've got the second quarter here, you've got the third here and the fourth here. The points in between the quarters, so that is point D, point C, and point E. Those are the points in between the quarters. Those are known as your quartiles. D is your first quartile. E is going to be your third quartile. And the median itself is always your second quartile. So again, this is your first quartile, your second quartile, your third quartile. They are the division points between, the separation points between each of the quarters, first and second, second and third, third and fourth quarters. And your interquartile range is going to be your Q3 value, which is E, right? This is Q3, Q2, and Q1. Q3 minus Q1. That is your interquartile range. That is really all you need to know for box and whisker plots. If you know this information, these questions should not be difficult at all. In fact, they are probably some of the easiest questions on the test. In terms of shape of distributions, what we're going to do here is we're going to draw a bunch of distribution shapes. The first of which will be what is known as a perfectly symmetrical distribution. I'm not always so great at drawing these, but that actually came out pretty well. So this is a symmetrical distribution. Let's draw these and then we'll give a little bit of a background on what these are. In terms of the next one, we're going to do what is known as a right skewed distribution. That also didn't come out too badly. Right skewed. Let's do a left skewed. That will be left skewed. Now, by the way, in terms of the skewed, some students look at this and think, why is this called right skewed and why is this called left skewed when the hump is on the left here and the hump is on the right here? We're not looking at where the hump is. We're actually looking at where the tail is. So this has a long right tail. And by tail, I just mean this long sloping part of the distribution curve. And then this one has a long left tail. So again, it's where the tail is relative to the hump. If the tail is on the right, that's right skewed. If the tail is on the left, that's left skewed. We can also have a uniform distribution, which would basically be a big block like that. So that's uniform. And one that you probably won't see on the test, although we did see something that looked like this on that dot plot. You might see something like that, which we would call bimodal. So here's what's happening here. Just like with a dot plot, just like with the histogram, we've got this vertical axis that represents a frequency or a probability of a certain value occurring. So the higher the curve, the higher the frequency or the higher probability of a certain value occurring. So for instance, whatever value would be right here, that is the value that occurs most often or that has the highest probability of occurring, which, by the way, means that value there is your mode, because mode is the most common or most frequent element in a set. So here's what we need to know about this first row of distributions. In the symmetrical distribution, what will end up happening is that mode will also be your median, and it will also be your mean. In other words, all of the measures of center in a symmetrical distribution are in exactly the same place because the set is perfectly symmetrical with respect to its center. All of the elements are symmetrically distributed around that center, which means there will be no pulling of any of these central tendencies to the right or the left. Now, when it comes to a right skewed, and we did see this before, or something that kind of looked like a right skewed data set, what will happen is that guy there, the peak, the maximum value, will still be your mode. Because again, remember, mode is the element that occurs most frequently. So whatever data point is right here, and by the way, again, the x-axis would be our data values or data points. So the mode would still be at that peak, but what would happen is because we have more of our elements situated to the right of that measure of center, what's going to end up happening is that our median and our mean will both be pulled a little bit to the right. So for instance, the median may be here, just a little bit to the right of the mode, and the mean will be pulled even farther to the right of the median. And we did see that on the dot plot question. With a left skewed distribution, same thing, but kind of in reverse. Mode will still be the highest frequency element. Median will be pulled a little bit to, median will be pulled a little bit to the left, and the mean will be pulled a little bit to the left of that. Let me get rid of this. So there would be your median. And again, these are just approximations. I'm not giving any concrete numbers here. You just need to know, for the purposes of these questions, you would almost certainly just need to know some generalities, some relative positions of these measures of center. When it comes to a uniform distribution, that just means that every single data point has exactly the same frequency or probability of occurring. A really good example of a uniform distribution would be rolling a dice. If I just keep rolling a six-sided dice over and over and over again, let's say thousands and thousands of times, what I would expect to see, I don't know at all how the values would be oriented here, so I'm just randomly drawing a 1, a 3, and a 5. Probably wouldn't be that way if you were actually looking at a real dice, but that's okay. If I just keep rolling this dice over and over and over again, I'm going to expect to see the same number of, here, I'll even draw some bars in here, almost like a histogram. So 1, 2, 3, 4, 5, 6. I would expect to see the same number of 1s, same number of 2s, 3s, 4s, 5s, 6s come up, unless this dice were weighted in some way that caused a certain number to come up a lot more frequently than the other numbers. I'm gonna see 1, 2, 3, 4, 5, 6 showing up, or on the top of the dice the same number of times if I roll this dice a bunch of times. And then of course with bimodal, you can see it in the curve. You've got one mode here, you've got a second mode here. Technically a set can only have one mode, but when it comes to distributions like this, we would call this set bimodal because there are two values that occur most frequently and therefore account for the two humps in the curve. So that is shape of distributions. Again, you are most likely not going to need to know anything too complicated about shapes of distributions. There's a chance that you may need to incorporate some information about standard deviation and a distribution curve. If that happens, you most likely will just need to know what we talked about in terms of standard deviation and distribution from this section, and then a little bit of information from the section in which we talk about data studies and conclusions from data studies. That is it for measures of spread and shape of distributions. We will be moving on to some ways that we can use our calculator to help us on some statistics questions like these.